We're supposed to start with Matias Bjørling on Open-Channel SSDs to Zoned Namespaces. Unfortunately, he couldn't make it, so as one of the program committee co-chairs, I'll just fill in for him. And it helps that I've worked with him on that whole thing, so that makes it a little easier. And because I'm not him, I can skip over this marketing and legal stuff and get straight to the point. And when we talk about Open-Channel SSDs and the follow-ons to it, I think we just need to start with the quick 2-minute, 10,000-foot overview of how a SSD actually works. And we could spend days on that, but let's just do the very basic overview. So if we're talking about an SSD, we got something that to the host OS, the application looks kind of like a disk drive, a little less now, but kind of sort of. And underneath, it's dealing with NAND flash, which is very different from the traditional disks in that you don't just read and write wherever you want, but you read and program and erase. So you need to erase your block first before you can write to it. And you do that in a relatively large block size that's keep getting bigger and bigger and bigger and bigger, and also has kinds of weird interdependencies with things around it these days. So when we talk about an SSD, we got a lot of these NAND flash dies. For typical SSDs, it's in the tens. For a little device, it could be less. For some giant devices, it might be more, but that's a pretty good approximation. And to give the regular read and write semantics, there is a whole lot of overhead running on that SSD. That's doing a translation layer between the little logical blocks we see up there to the intricate details of the flash. It's doing some weir levelings because flash is actually wearing out every time we write it. Actually, sometimes when we read it too, but that's another different story. It collects the garbage when we wrote a logical block again and now had to write to a different physical block because the old one wasn't rewritable at this point. So we keep writing it to a different place and have to clean up later. People from the file system world that have done log structured file systems might know all the problems about that, or people who've been doing SSD architecture. Then you got the bad block management, media errors, which are usually due to bad blocks, but could be other things, and so on and so on and so on. So we've got this big blob there out of a couple of different pieces of functionalities that translates between reads and writes a traditional file system or database uses to access the storage into the world of physics down there. And when we're talking about an open-channel SSD, we're talking about sort of a bit of a cloud of concepts that expose more of that hardware reality to the operating system and or application. And in this talk, when we're talking about open-channel SSDs, we're kind of talking about the OC SSD spec, which comes in a couple different versions that have evolved over a while. But the idea is that you take your LBA range in a traditional disk that was just a sequentially numbered chunk of blocks, which was a huge improvement over the old disks that had their weird geometry-based addressing, and actually throw in some geometry-based addressing again, because now it makes our life easier. And in each of these chunks, you write sequentially. You need to delete all the data in that chunk together, which we sometimes call a reset because it resets it to the original state. And a lot of these concepts are kind of aligned with some of the modern hard drives do when we're doing shingled magnetic recording, when the recording tracks on the drives are so close that you don't want to randomly rewrite them because you would get physical interference with the atoms next door. And there's been a specification out for that for quite a long time, which is the zoned block devices in SCSI and the zoned access command, or whatever is the equivalent in ATA. Damien probably knows the full name. Zoned ATA commands. And in addition to this kind of logical-ish concept, there's also the other axis to it is how do you actually place the data? Because if you look at how the SSD is built, we've got these dies hanging off certain channels, and you have a lot of parallelism constraints of how much is going on a given die, how much do you load a given channel. And because of that, the Open-Channel spec also exposes something very close to the physical layout, and the application or the file system or the volume manager actually has to do exact placement. And Matias says it's kind of similar to I/O determinism in NVMe. I disagree a bit. I mean, it's trying to do the same thing, but this one is doing it straightforward, but very, very low level, probably too low level, and the NVMe I/O determinism is doing it in a very confusing high level way. So they're kind of the same point, but not the same thing. Yeah, more fluff. More fluff. Okay, now back to technical points. So one spec that Matias and I and a few others have been working on now in the NVMe working group and a little before is to look into a concept called the zoned namespaces. And this is, well, this started out as a one-to-one mapping of what ATA and SCSI had been doing for their zone drives. So we keep doing what's on the most left-hand side before the fluff. So we still separate our drive in all these chunks, which, just like the disk standards, we call zones, just because that sounds so much better than chunks, and it's been chosen before. And in these chunks, or zones, you must write sequentially from the first logical block in it to the last. Well, you don't have to write the last. You don't always have to fill it, but I mean, every block you write has to be sequential to the previous one. And when you want to rewrite it, you have to delete the whole thing first. For the file system people that read the classic block structured file system papers, they call it a segment, but it's all the same thing, basically. And this is kind of the concept we're talking about. And then there's another bit that's going on in the NVMe spec, which is kind of bringing in the other half of what the OC SSD spec is doing. And that is all about doing physical-ish placement of your data versus the hardware components. But that's done in a different technical proposal in NVMe, and we're not really covered here. It's just mentioned for completeness that people are looking into that bit as well. So, yeah, when we're talking about the zoned namespaces, what's the point? And some drive guys might just tell you, oh, it's to reduce all the DRAM you otherwise have on the SSD, and I'm pretty sure that's a nice side effect, but we're trying to sell this because it actually makes the host's life easier for, well, a couple use cases at least, hopefully a lot of use cases. And one of the nice bits of this whole explicit delete scheme that is very close to how the NAND hardware works is that your host is very much in control of the write amplification that the SSD would have to do underneath. So if you think of the fact that you have an LBA number 42 and you just keep writing to it again and again and again and again because you're using an old Berkeley fast file system or XT234 that's just writing the super block or the block cylinder group headers again and again, that means for the flash device, it has to remap it to a different place every time, creates a hole in its other physical block, and we just massively increase the amount of data we need to write because we need to keep track of it. While on the other hand, if your file system is aware of how the flash works, it might be smart enough to not just rewrite that block again and again and again just to increase a little counter because it might figure out it can actually do without the counter, or it can throw in the counter into something that it has in the file system lock and bundle it together with other updates, or so on, or so on. I mean, at this point, we're getting into file system design for these kinds of devices, which is another whole interesting topic. If you care about that, join us in the NVM BOF tonight. And The other interesting thing is about latency and service isolation, because one of the nasty things the whole background operations and normal SSD does in terms of writing out of place, garbage collecting, is there could be a lot more latency than what you expect. I mean, one is the raw flash latency. How much does a program take? In fact, for the enterprise SSD, you usually don't even care about that because it's buffered in SRAM first, but that's another different story. But your program and erase cycles might conflict with reads to the same die because they can't be executed at the same time. And there's some devices that can do suspends of the reads, but it's a lot of action that happens in the background that the host doesn't even know about. While on the other hand, if you have a zone that you explicitly write, which is the program, which you explicitly reset, which is the erase, and have a little bit of the underlying isolation, which was done in that other proposal I briefly talked about and we're kind of ignoring here, you can be relatively sure that no one's getting in your way. And this should help with latency outliers. Now, if you talk to some traditional SSD architects, they might be of the opinion that they can very well mitigate it, and they might be right, but it all comes at a cost, even if it's literally just a cost in the terms of dollar spend. And what this leads to is, in general, a much, much simpler SSD architecture if you expose more of the characteristics to the host and you avoid the problem that you need to do a double translation of the logical block as you see it in your file to a physical block in the file system to a actual really physical block in the SSD. Never mind talking about any other remapping layers in between in a storage array or hypervisor or whatever people throw in. Yeah, so we're getting back into the basic zone concepts that we already started on a little earlier, and at this point this is all taken straight one-to-one from the existing SCSI and ATA specs. So the disk, or in the NVMe case, the namespace, and SCSI, the logical unit. In ATA, there's only one thing behind the device anyway, so that's simpler, is divided into our zones. Each zone is of a fixed size, so in the disk drives, it's usually 256 megabytes, but that's by convention, not by standard. It could basically be any size. Also, the host vendors would really appreciate it if it's usually a power of 2. That makes a lot of things much, much, much easier for the host. Not necessarily for the SSD, but that's another interesting side story. Each of these zones is written sequentially, and each needs to be erased together. I mentioned the third time today, should stick now. And then down here, we have the state machine. So we were kind of already getting into the basics of that. So your original state, and I'll just jump down here to point it, is an empty state. So you've got a zone. It has no blocks written to it. It is not filled at all. The write pointer, which shows where your next write has to go to be sequential, is invalid. You then either implicitly open it by just writing to it, which is one of the two models that we picked up from SCSI, or actually I think I get a bit of an echo there, so I'll move away there, or you do an explicit open with an open command. There's two different models that go all the way back to the SCSI and ATA specification, and the idea behind it is with an explicit open command you can kind of preload the latencies to start a new one, which at least in the disk world so far haven't really mattered much, if I understood Damien correctly. With SSDs, they might or might not, depending on how the implementation looks like. Once you have that, you have your zone in an open state, well, in one of the two open states. Then there is a state that is somewhat misnamed, but again, the name came from the SCSI and ATA world, which is called closed. Really should be more something like paused, because it's a zone that is not fully written to, where the write pointer is somewhere in the middle of it, but the host tells the device, okay, please don't expect any write any time for it, release any resources, move it from SRAM to DRAM, move it your table somewhere, but I might come back to you later. I might just take a latency hit when I get back to it. And once we've written everything in there, the zone transitions to the full state. The full state means, okay, we fill it all now. There's no need to keep any resources in firmware, in hardware, in anything. We're done. The only thing we're going to do from now is reading from it or eventually reset it. And then there's two kind of magic wonky states on this side of the state diagram that can only be entered by unspecified vendor-specific means. One is read-only, as in you can't ever write to this again, but you can still get your data out, which, at least in theory, kind of makes sense for hard drives. I don't really see how this is going to work for an SSD, but we kept it in there. And the other one is offline, which means boom, poof, it's gone, the device broke down, don't ever use this again. And again, this is no standard way to get in there. These are basically error conditions. And yeah, we actually had another half slide that was talking about just about everything I was just explaining. And the other interesting thing, and this is where the zoned namespaces start to differ from what's currently in SCSI and ATA, is that we have a concept of a zoned capacity that's different from the zoned size. Who's used to SCSI logical block provisioning or thin provisioning, as we used to call it? Yeah, so this is exactly what we're getting into. So we have a zone that has a size in logical blocks, how it appears in the namespace, that is a nice round number, so that a host that might be implemented in FPGA or very low end can do a little bit shifting and get to it. But the actual capacity might be less than that because that aligns so much better to how that flash might be laid out. So for each of these zones, you might only be able to write 482 megabytes out of the 512 that it logically shows up to. And if you write beyond that, you get an error. There's actually some people like Intel that are pushing for another mode where the device can decide that at any point it doesn't have any capacity anymore, even if it didn't tell you before, which is not going to make hosts very happy. So we'll keep that as an option in there for people who really want to implement it, and then they have to find someone to actually buy these devices. So I hope it's not going to be many. And now comes the second new invention compared to what is there in SCSI and ATA. And Fred Knight, who's here, but I think at FAST, reminded me there actually was a proposal about this in SCSI, but it didn't go anywhere. So we're not the very first. I mean, in fact, at least this version is also based on an old FAST paper, which was not specific to zone devices. But anyway, I'm distracting. Getting back to the point. The zone append command is a command that writes data to a zone and writes it wherever the device wants. And the device wants it at the current write pointer so that it's sequential, because if it wasn't sequential, it would have to reject the I/O. So why do we want to do that? The problem is with a traditional I/O model that we have everywhere. So when you're running a Linux or a Windows box or for just about everything but a few databases, you tend to have multiple I/Os outstanding at a time. Queue depth larger than one, because that's pretty much the only way to get all the performance out of your device. But if you have a device that requires strictly sequential writes, you have a problem, because now from the time where your file system allocated a block number to the point where that I/O makes it to disk, it must never ever be reordered, because if the first I/O that has the lower blocks gets to the device later than the other I/O that has the higher LBA numbers, you're not writing sequential. And you have a problem that is really, really hard to handle, because now the error handling means you need to wait for the device to return you an error on all of these, figure out if it actually changed the write pointer somehow during that, which it shouldn't, but who knows, and try it all again. So you're in a deep, deep problem. What this leads to in practice is everyone who's using the zoned disk drives is writing with a queue depth of 1 per zone, not per device. The device has many zones, so you can still have one I/O outstanding to each zone, but you can have multiple I/Os outstanding to a given zone, which can be pretty annoying if you're doing something like a block structure database or file system that's just writing to a few zones at a time and has a lot of I/O bandwidth outstanding to it. The performance is just not going to be great. So that's why we've looked into the zone append command, which, as I said, is a bit of a variation of the nameless writes that were proposed in FAST, I don't know, 8 years ago or so. And the idea there is that the host sends the device a command that says, write some data, and then the device tells the host in the reply, in the completion of the command, where it wrote it. And in the original paper, it was kind of, okay, you write it to the device and it places it anywhere on the device, which is kind of very flexible for the device, but it's actually really bad for the host because the host usually has some form of sharding to get parallelism out of the device, which we call allocation groups, block groups, cylinder groups, segments. People got all these names for it. And if the device can just place the data anywhere, it's pretty bad. But now that we actually got these zones, because that's the unit of granularity where we can write sequentially, they're actually a very nice shared concept of a boundary between the device and the host. And the host can nicely align its own sharding to a zone or to a small multiple of zones. And it's perfectly happy to just direct its write to a zone and doesn't really care where in that zone it lands as long as it's, well, accepted by the device because it's written sequentially from the device point of view. And yeah, it's actually very simple NVMe command how we defined it. So instead of sending down the LBA you want to write to, you send down the first LBA in the zone, which is used in all the zone commands and the 3 standards to identify a zone. There is no separate zone identifier. And then in the completion queue entry, you just get the LBA back where the device wrote it. And at that point, the file system updates its metadata to find that data, which it has to do after the I/O completion anyway to avoid stale data exposure races. I mean, some of the 80s file systems don't do it, but that leads to stale data exposure. So everything modern can only update the metadata after the I/O completion anyway. So this fits very well into that model. And yeah, so we got a couple examples, lots of funky graphics. So 4K write to the beginning, another write at 8K. Then we get another write. The write pointer just keeps moving back with every write. Everything's fine so far. And with the zone append, all of them just point to the block 0 in the zone, but that actually gets updated after the completion. So big question is, why do we do it like SCSI and ATA did? I mean, one, it's much easier to do a standard if there's one you can copy it from. Some people might know that from their term papers. But except for that, I mean, the other big advantage of staying compatible is just there's quite a bit of software enablement for the SMR drives. Damien wasted the last 10 years of his life on that. And on some of the 2&me. And so there's a lot of software that's been dealing with the pitfalls of zone devices and is finally getting to a mature state. So we really don't want to start that again and again and again with slightly different concepts. So in Linux, which I'm most familiar here, and well, we're at Vault, so most people should, or at least interested. Our storage stack, we've got quite a few layers that are dealing with these zone block devices. So we've enabled the low-level SCSI disk driver. We've enabled the ATA driver, which kind of hangs under SCSI to translate that, but that's sort of the trivial bit. And then we have a device mapper zone block device, which is basically a very, very trivial FTL in the kernel as a device mapper module. I think of it more as a stopgap for people who want to try it out, because once you just replicate what you lifted out of the firmware in the kernel, you're not going to win that much. I mean, your DRAM might be cheaper to acquire in DIMMs for the host system than embedded on tiny form factor SSD, but that's about it. I mean, this is not the big win if you use that. The more interesting case is either when you do pass-through and have an application directly using the zone block devices, have your user space, file system, database that is really architected around this. And I know there's some customers doing that with SMR drives, or if you have your regular kernel file system enhanced with support for these zone concepts. And for quite a while, we have F2FS with a full SMR enablement in the Linux kernel. So that's the Flash-friendly file system. It's shipping on a lot of Android devices, and it's a file system that basically can write everything sequentially for data. It still needs a random access region for metadata, which the disk drives generally support in addition to the sequential bit, which for NVMe would either have to be a separate namespace or a separate device, but the file systems, well, F2FS and others I get into later, generally support a multi-device setup. The second one that Damien's long-term intern and now new hire has been working on for a while is ButterFS support. ButterFS, again, is a file system that can and often does write out of place. Just need to fix a lot of the issues about really being strictly sequential and not just out of place, and that's actually progressing very nicely. I've been doing work on XFS, which is actually traditional write-in-place file systems, but a couple years ago we did out-of-place write support for data deduplication and ref links, that is file cloning, and that can be really nicely reused for always writing out of place. And the first milestone of that has just landed in the tree for the next merge window, but there's a lot more work to do. And once you do that direct integration, you start saving a lot of DRAM, and you should also save a lot of write amplification. The better utilization of the SSD, I put that with a question mark, cannot be. I think that requires a lot of optimization for the actual workload. Yeah, so we got a lot of this already going. And yeah, it's just listing the projects. Most of those already did. Got the state model again, and I think we're done. Thank you very much for listening. I'll put my Matias voice on. So in ATA and SCSI, the state remains where it was. Oh, repeat the question. Yeah. So if you're doing a controller reset, or I guess a power fail, or any kind of unexpected condition, what state are the zones in that you previously had open or closed? So the ATA SCSI answer that is in the current draft of ZNS is they stay the way they were before. So the firmware needs to persist those. We're thinking of changing that to better reflect the flash realities, but it's not finally defined yet.
Yeah. Is this stuff going to use the regular block stack for things like zone append, or is it going to bypass the block stack? And do we worry about things like the block stack will split things at 1 megabyte, at least currently?
So all the existing zone stuff is in the block layer in the broadest sense. So a lot of it is just a different bio operation. For the zone report, which is the one that reports you the state of the zones, we moved it away from a bio op to a real method call because that was much easier to handle with the different kinds of payloads. And for the zone append, I have a prototype for that right now. It's yet another bio type. It's marked as no merge, no split. You have to submit it the right maximum size. And then the driver updates the sector that would normally be an input parameter from the zone stored LBA to the one it actually placed it.
Thanks.
So for magnetic drives, the SMR technology allowed the cylinders to be put tighter together to get more capacity on the drives. What are the technology applications for zones for NVMe? What does it enable? Right.
Well, this was kind of what I was trying to get in the beginning. I mean, one big thing is just cost reduction. I mean, if you look at an SSD right now, I mean, at least an enterprise one, not necessarily the cheapest consumer ones, it has a huge load of DRAM on there in addition to the flash. If you can't save that DRAM, you reduce the cost, you increase the density. and so on. And the other bit is, I mean, even if cost wasn't an issue, it's still wasteful to have duplicate translation tables instead of one that goes all the way down. It could allow you to do better isolation, better latency containment, and so on. It's basically a lower level control that's closer to how the storage medium actually works.
Thanks, Christoph.